Samantha Porter. I'm a member of the User Assistance Team here at Oak Ridge National Lab at the National Center of Computational Sciences. My goal today is actually very, I decided that I was going to do a very high-level talk, sort of talk to you and walk you through, for example, when I'm compiling something, what I'm thinking about, and the things I know that compilers do. In the last year, for example, I've been to participate in the standards committee for the OpenACC standards, and that's been really interesting in learning how the committee is made up from people and users to compiler folks, and they're the ones really that are implementing whatever standards in the language go into the compiler and how they're going to do it. Sometimes I will ask for things where the compiler developers will say, well, that's really hard to do. I would love to do that, but this is going to take 6 months, and we're not going to be able to put it in this release. So can we table it for the next release? And then, or talking about how it might work and how it may not work, and scenarios why it wouldn't work. So it's been really interesting to understand how compiler developers think during this process and how they're thinking about optimizing and the possible failures that could go, possible things that could go wrong. And so when I've had experience in not only developing applications, but I've had experience in developing scientific applications, let's just say. I don't know how to make other applications, but scientific applications. And I've had experience in trying to do better optimization especially for the kinds of things that run at our center, right? It's very important for us to make sure that we get no wasted flops, no wasted instruction, and keep data movement to a minimum. And so all of those things make the computer wait and make the clock cycles go wasted are sort of the things that you're looking for when you're developing an application and you're developing it for speed and efficiency. All said, compilers do a very good job at that. And so often when I teach and when I tell people how to write applications, I tell them that sometimes their best bet is to write the naive way, to write the dumb way, to write in a way that a compiler will see what it is you're trying to do and pick that up. And so often you'll think, part of my code isn't being optimized, and you think, well, this compiler isn't good enough. Maybe that it just doesn't see what you're trying to do, and so it can't sort of see the pattern, right? So I know that you might have used the compiler before, but we go back, take a step back. Those that want to sort of understand the thinking of compilers and how compilers see your program. So I want to take a step back. Let's see. Oh, that's where I work. I put a picture up and I forgot to move forward. This is not how a compiler works. I like this picture primarily because it was one of the first calculators. Somebody needs to get muted. All right, we're muted. This is the first computers, and back then they had to write, instructions that were very, very specific, and some of those connectors actually do connect things. And so we don't have to write at that low level, right? They had to write at a machine language level. We don't have to write at this today. We can write higher level. So that's essentially what a compiler does. It stops you from having to write for this. And it lets you write in a language that is probably easier for you to express your ideas, express specifically scientific functions, scientific procedures, scientific things. I don't know, math, and then turn that into machine code. And that sounds pretty magical in itself, and it could do that very naively. It could just say exactly what it is that you wrote, and it could just put that into machine code as bad as you might have written it. But that's not all a compiler does, right? There's some magic in the middle, and that magic in the middle is what I'm going to try to get you to focus on not to think of the machine language part, but to think of how can I communicate a little better with that magic in the middle, that special sauce that each compiler vendor puts out there in a compiler. So compilers have what's called a code optimizer, and that's a special sauce. That is what it's called. It reads what you've written and determines what can be optimized. It writes what's called intermediate code, analyzes that intermediate code, and then repeats the analysis again. And so it keeps doing that, and it sort of does that, over and over. So large codes, sometimes we have here some codes that go into, 500,000 lines. It takes a very long time to compile. It's the sort of thing that you set to compile and you walk away from your chair and you hope it doesn't have an error, and then you do it again. But the key, and what I want to keep saying, is the more obvious you make your intention, the better for that code optimizer to see what it is you're trying to do. Often what I'll see in scientific code is that scientists try to either write very exactly what it is that they're trying to do, it's maybe some sort of special equation they've come up with, and their special sauce for their special science, and they'll put that there, and the compiler has no idea what they're trying to do. So if you can find a way that it doesn't have, for example, maybe dependencies that the compiler can see, it can move things around and it can shuffle a little bit better. Maybe it can do some things that are asynchronous, not in the way you wrote it, right? Maybe you might have written that procedure so that it would do A, B, and C, but maybe B doesn't need to be done until later. You can save a little time because it doesn't have to shuffle memory around. A code optimizer, if you've written it obvious enough without so many dependencies, would be able to see that and then move that around. It mainly does it through two methods, or at least there are two large things that it tries to do. It tries to control the flow. It tries to do some optimization on how you've written your code, right? So procedurally, how the code moves forward and backwards, and also some data flow control. So whether or not you're allocating, you say you want to allocate that array right now, but actually you don't use that array until much later in your code, the compiler is going to see that, and it may be smart enough to say, we don't need to allocate this right now. I'm going to move this instruction all the way down because it's going to be better. So it also tries to do some data reuse, so it looks for the ability to reuse data when you can. So if you're doing some sort of calculation that you're using a variable and then you reuse that variable in the next instruction or 3 instructions down, and if it can see that those instructions don't depend on each other, it'll try to move the instructions around so that it can reuse what's already been loaded into cache. And cache operations, again, making sure that you reuse cache, because every time you have to go try to find a variable and that variable isn't there, and you have a cache hit that misses a cache hit, it has to go out into slower memory to go fetch that. And so those are some of the things that a code optimizer looks for when it's optimizing your code. Now, all of the compiler vendors do this differently. All of them focus on different bits. Some of them focus on flow control. Some of them focus on data. Some of them don't focus on things that are important for the kinds of applications that you're doing. That really is going to depend on the compiler, and part of it is perhaps understanding what the compiler vendor, or at least one should understand, if you want to get the maximum kind of optimization from your compiler, one should understand the audience that compiler vendor writes for. So perhaps a compiler vendor that may only sell the compiler for Windows applications, to build Windows applications, might not be necessarily the best if you're writing Linux applications. Those are just some of the things that you might want to sort of keep in mind, keep in the back of your head. What kind of application am I writing, and am I using the right compiler that focuses on these sorts of optimizations? And obviously, we're talking mostly C and Fortran for scientific applications, but there are lots of other compilers. In fact, this weekend I was just joking around about Pascal compilers, how Pascal used to be able to do inlining of machine code. But maybe I'm old. So function inlining. Here's a something that our compiler does that you can make, for example, far more obvious for the compiler. Timing is every time you have to do a call, that call requires an instruction. So it requires it to know, for example, where that call resides and where the pieces of code that it's translated into machine language reside. So it has to go somewhere, and it has to go fetch that. A compiler, if you can make it pretty obvious that that function call should go here, and it's worth its while to inline it, then you should make it pretty obvious. Sometimes it'll have maybe thresholds, like if the loop is too small, if the function call is just once, the compiler might not do that because the cost of going to get a function and coming back and giving you a result isn't going to be that much bigger in the grand scheme of things. But if you have a loop that goes over hundreds of thousands, the function calls begin to add up, right? So the times begin to add up, so it makes sense for example, for the compiler to inline that and bring that in. And here's just a simple, dumb example of that. Obviously, the smaller the function, the better. It can actually inline, I mean, some are good enough to inline small subroutines or even functions that are really big. The problem with that becomes then it's just the binaries get very big. And you might think about that because on certain systems, for example, on Titan, there's a limit to the binary size. And so if your binary is beyond a 2 gigabyte limit, it can't go on the compute nodes, and you can't run your job. I don't think that I've really ever come across a binary that's 2 gigabytes, but I know that has been an issue for users here. And some of these code bases are pretty large. And please feel free to stop me at any moment to ask questions. I wanted to say that in the beginning, and I forgot. Loop unrolling. You've seen this when you compile. You'll see it that sometimes it'll pick up that it can unroll a loop. Often what happens is if you write a loop in a way that the compiler can't tell when that loop and it's not a definite loop, for example, it's an undefined size. Maybe you have a while and it's always checking, for example, for a certain value. If you're writing that sort of loop, a compiler can't tell when that loop ends. If you have certain breaks, for example, in a loop, or you say do this for a few times and then check something, and if it is that something, then get out of this loop. A compiler usually tries not to unroll that because it doesn't have a definite size. Therefore, it doesn't really know what best way to optimize that. You know what a loop unroll is. I mean, if you don't, here's what it does. It removes the overhead of checking if the loop is done. So it rewrites this in a way. Actually, I have a mistake here. That should be I to 10, I less than 10, not 50. But what it does is it removes the overhead of having to check, am I done with this loop? Am I done with this loop? And every time it loops around, it has that overhead. And so now, instead of having to do that, I would only have done that maybe 10 times as opposed to 50 times. But if your loop is ambiguous in its size, or if your loop has breaks, for example, a sudden breaks where you say, check for this, oh, get out of this loop, then the compiler really can't do that. And so it leaves that loop alone. So this is something that you can do in your code to make it, again, obvious for the compiler. The compiler's kind of dumb. It's not very sophisticated, and you can see that right away, and you can optimize that loop for you. Instruction optimization. Here's something I see actually very, very often. Often when scientists write, they'll write either a loop or a function. They'll write it very much in how they're thinking. First you do A, then you do B, then you do C, and they kind of put it in and say, oh, I need to do this times. And then they don't realize perhaps that they've added instructions they could have removed from the loop. And so you're doing extra calculations that need not be done. If you write this in a way that has very little dependency, in other words, maybe it doesn't depend on one of the loop integers, or it doesn't counters, or it doesn't depend on anything else that's on the outside, and that's something that you can, again, remove by yourself or make very, very obvious for the compiler. Sometimes it can be something as simple as somebody's writing an equation, for example, that calculates the log of a certain value, and it calculates the log twice. and you can maybe pre-calculate that value. Pre-calculation is something that you should do in your code anyway. Don't expect the compiler to do it all the time, but it always helps when you write it for the compiler so that it can pick those things up. So inlining small routines and moving code out of loops that are unnecessary. And so the point of this, obviously, is to have the loop be picked up by the compiler for optimization. Flow analysis. So depending on the flow or the path of the data, they be reused. For example, if you have different variables that you've determined, but they point to the same location, or they, you might have different variables that point to either a location that gets reused. It may know that you're trying to use a specific value, and then you keep calling that value from elsewhere. You keep going to look for that specific value. It may create a temporary variable for you, so you don't have to. So that temporary variable resides in a lower cache, local memory, local to the CPU, and it doesn't have to, for example, to go out and go fetch that in some more global memory, slower memory. The key to writing good programs today, it really isn't even focusing really on the flops. It's really focusing where the data is. Data locality is actually one of the things that make programs the slowest today. Improving your data locality is really, flops are free. If everybody can sort of get that in their head, flops are free. I can actually calculate things, more things than I need, but moving data means that the CPU tries to go look for something, and then it says, it's not here where I thought it was. And then it just kind of sits, literally the CPU just kind of sits in a little loop, and it just kind of waits for that memory to come and get loaded. And when it sits in a loop, it's time that you're wasting that you could have been using to calculate something else. So different variables that point to the same location, or shuffle instructions for variables that don't depend on each other but avoid, for example, this extraneous movement of data. Some compilers can actually be very good about removing dead store. Dead store is often I'm laughing because I remember one specific piece of software that I was optimizing, and this person had allocated several arrays that were temporary arrays from when they were doing the calculations, or when they were doing the application, when they were building the application, and then they forgot to remove them from the original allocations, and so all these arrays were getting allocated, and they weren't allocatable arrays. I mean, they were built-in arrays, and so all this memory was being used that wasn't being used later. And I remember working with the user on that and saying, okay, let's make sure that this is not something that you really need to use. And then there were lots of checks, for example, are these values correct, or is that value correct? Those are the sorts of things that you can maybe put it in a separate routine that you can then not call later when you're done debugging your code. Branching. This is something that helps if you understand a little bit how architecture and how compilers are built. Branching is a pretty big hog of time. And the reason why is because when you do, for example, if-else, the way a compiler writes it back into machine code is it'll actually follow both branches until a determination is made. That was surprising to me when I learned it way back when, and it's something that still surprises a lot of people, I think. And so, for example, if something says, if this is A, do something, else do something else, it doesn't know which one it's going to be, so it actually writes machine code that follows both branches until that is determined. And it tries to guess. What it actually tries to do is it tries to guess which way it's going to go. And the guessing algorithms can get really complicated. So branch guessing is something that's kind of big in the compiler research world, where it tries to edge out. And often they can be as right maybe 80% of the time, but the 20% of the time it's not right. The 20% of the time you could be doing something else with that computer time. Not shuffling memory, not doing, again, memory's costly. So if you can rewrite your branching into either things like case statements, or if you can rewrite it in a way that you don't have to do branching, that's, ideal. So again, branching is something that can, it's something that probably should think about minimizing in your code if you don't have to. Okay, so we're at 33. Any questions at this moment, or? No? Okay. Vectorization. Vectorization is something that was originally how computers were built. They were built as vector machines, very specialized cores, and then we sort of got away from that, and then compilers took over vectorizing code so that it would fit into the CPU instruction in a way that was efficient. Now, remember, it takes time for a loop to do a check, and that instruction, that's instruction that takes time. So every time it has to go through the loop, it has to do a check. And every time it goes around the loop, it also has to load the instruction and then load different bits of memory. Whereas if you vectorize your code, all you have to do is just the vectorization process is now it writes the instruction, and then goes and fetches the memory. So it just, instead of having to read the instruction and decode it, it just writes it straight into the core, and then it loads those bits of memory, and then it goes on to the next one, and it doesn't have to do that extra looping. Flags, I wanted to talk about flags a little bit, and I put the top here. This is actually from another presentation. I really wanted to do more with flags on the presentation end. I literally ran out of time today. And so what I wanted to talk about flags is, flags can get very fancy. There's tons of flags. It helps if you understand what your hardware target is. It helps you if you understand what these flags do. So a lot of flags actually can be a combination of several flags that you could do together. For example, an O3 you might have all the flags included in an O2, and then it has more aggressive loop transformations, right? The thing that I have about flags is that some people forget, for example, they'll leave their debug flag on. I see that often, where they compiled everything with a -G, and then they say, well, my code is really slow. Well, it has all those extra instructions that have been there to give you their error output, to give you more verbose output when something goes wrong. There are some flags there that sound fantastic, like auto-parallel, auto-parallelization. You probably want to avoid some things like that. There are some flags that are specific to the instruction set that a CPU uses, and those are really good to have. So if you're using, for example, an Intel compiler on an Intel hardware, you want to look for the flags that will give you extra instructions and use all of the available instructions on an Intel chip. And now, some compilers will go all the way, some compilers won't. I mean, these are standard sets of instructions. That there's a standards body out there that has these things. But some of them will perform poorly. And if you're going to, for example, use an Intel compiler on an AMD CPU, it may perform poorly because it's a vendor that's outside of Intel, and it's not something that Intel specializes in, and may or may not have those instructions. So it's important that if you decided on a set of flags, if you move later on to another CPU or another piece of hardware, that you check again those flags, because they may not, for example, have AVX, it may have SSE2 and not 3, and you have to recheck things that you've added to it and what the optimizations that have been added to it. Also check for default optimizations or default flags, and we can come back to it if there are some other questions about flags. Which compilers is important? Well, that depends. Not all compilers cover parts of the standard. Standards are sort of the wish list of things. So if you have a language out there that you're using, and maybe it's a brand new language, or maybe it's a superset of a language. If there's a standards body that says, I wish this language could, fly, and it could go around the world 3 times and then land again. Well, some compilers will say it'll fly, but it'll only fly once around the world and it'll land, and because that's maybe our goal, and we've got to focus on other parts of our compiler. Compilers like PathScale, for example, they focus specifically on scientific applications and high-performance applications. They may want to cover other parts of the standard more deeply than, say, some other part of the standard that has nothing to do with high-performance computing. So how compilers cover all the standards? Not all of them cover the same way. Maybe a language should be able to do this, but a compiler doesn't do that. Maybe compilers, actually, a lot of compilers, what I found, go beyond the standard. They'll try to sort of predict what's next. Remember when I was saying, we were having a discussion in the OpenACC body for the standard, and it had something to do with how data is managed. And actually, some of the compilers had already implemented sort of internally how data management could look like, because these are discussions that we were having. And so they predicted that this is something that was going to come out, and they were sort of playing with that idea. And in a way, it kind of helps us maybe use some bits that are a little bit ahead of the game. A lot of compilers actually will do a better job of implementing things that should be in the standard but are not in the standard. They also do better if you can match manufacturers. So, we know Intel manufactures Intel chips. We know that NVIDIA manufactures GPUs, and if you can use their compilers, you're probably going to be better off than using someone else's compiler. That is not to say that they're always going to be better. That is not saying that at all. I mean, there are other things that go into compilers, especially optimization. But in general, it's probably something that you want to take advantage of if you're really going to be focusing on the hardware that you're running on. Implementations vary from compiler to compiler, and some are more pedantic than others. Sometimes I'll compile something on GCC, and it compiles every time, and then I go to a Cray, and Cray is very, very picky about standards and languages and how you do things. And it'll tell you that it doesn't like it, or it'll throw an error or a warning. Some compilers will throw errors for things that are warnings in others. So just because it compiles, a very, very important piece of advice. Just because it compiles doesn't mean it's right. And just because it doesn't throw an error doesn't mean it's right. Some compilers leave you hanging, like it will not pick up things that you've done terribly wrong and terribly stupid. Others do better than that and say, hey, you're kind of, you might be dividing by 0 here, and the universe is going to explode. Some optimize better than others. I think we talked about that already in the beginning, but that's very important to understand that the point here of this bullet point is that you should probably use 2 to 3 compilers if you're really trying to sort of find an edge in your application and a little better. And then other compilers may actually be more verbose in what it is that it's trying to do, and they'll give you clues on maybe where you should focus on and maybe where you're not focusing on. So speaking of hardware, this is the machine that we have here. It's Titan, and I want you to notice a couple of things. Number one, we have AMD. We're not running Intel. We have a couple of other Intel machines here. And we're also running an accelerator. That's not the same hardware, for the same manufacturer as AMD. They're separate manufacturers. And so having to cross-compile is something that becomes an issue. In fact, Titan always cross-compiles because where people compile on Titan, they compile on a login node. And login node has a different architecture altogether from the internal compute nodes. So cross-compiling, if you don't know what cross-compiling is when you compile a piece of code and the output of that code has instructions for another piece of hardware that is not the hardware that you're running on. And so that's how you can download, for example, binaries off of somewhere else. It says this binary can run on this operating system. It is operating system dependent. It must run on the operating system that it was compiled for, but it also can be the less specific that the set of flags, for example, that you've put into your compilation can make it so that it's more available to different operating systems. So the less you try to be specific within an operating system, sometimes it can be just, if you're running a Linux x86 that's based on Red Hat, that's good enough for us. So it's kernel dependent. Anyway, so scientific applications here are cross-compiled to run on a compute node that actually has different pieces of hardware, and it is further cross-compiled for folks that are running code that run on accelerators. It's also important to note that there's very different types of hardware. AMD it runs at a higher clock rate. It also has a larger memory size, but that's lower memory than the lower clock rate CUDA cores run faster memory, that's DDR5. So those are some of the things that in the back of your head you might want to think about. It may be worthy enough if you're trying to get better performance to think about the types of hardware you're going to be running. And maybe it's worth it if you're doing a lot of memory operations. It may be worth it to move it to, say, an accelerator or to move it elsewhere because the memory might be faster. So architecture is important. Cache size is important. Cache size is really important. So CPUs have very large cache sizes. Some of the CPUs today have 8 to 12 megabytes in the lower caches, and GPUs have tiny caches, the kilobyte range. And so you can fit giant bits of instruction in the cache size. So it's very neat when you can optimize for cache size and keep that data locality. So if it fits within cache, and it fits within L2, and then it fits within L1, and it fits in L0, gosh, I don't even know if they have even more layers than that. But if they can fit into lower levels of cache, and you don't have to keep going to higher levels of cache to go fetch the next piece of data, the better. So thinking about how your data fits into cache is something that you can get a lot of performance out of. Special instructions. CPUs have a ton more number of instructions available than, say, a GPU. GPUs are intentionally sort of dumb little chips that can do calculations really fast. I like to joke that CPUs are great for you to be writing a report, surfing the web, and watching cat videos at the same time. And so there's lots of instructions there for the sorts of things that would require a lot of context switching. Whereas a GPU doesn't care. It only cares about drawing the next pixel. And so it doesn't need a lot of instructions. But more and more we're seeing that GPUs are actually adding instructions to their hardware, where each of, for example, the ALUs might be able to do instructions, like a CPU can do fuse, multiply, add, and a GPU maybe just multiply and add. Maybe one can do power and another one can't. And so special sometimes they have actually special hardware that can do those sorts of things. They can do power, they can do, I know that the GPUs can do square root, and it has a special, like a specialty little piece of hardware that actually do that calculation because it sees it so often in the sorts of calculations that it does for a video game, for example, when it's drawing pixels on the screen. Whereas a CPU probably doesn't care, so it doesn't include those instructions. It's important for you to know what architecture you're running on. If you're running a scientific application that requires specific instructions, especially math instructions, that aren't included in a specific architecture, then you're going to be doing that by hand. You can multiply, you can do a multiply, for example, multiplying two numbers and that be its own instruction, or you can just say, I'm going to multiply A and do it 5 times. I'm going to add that 5 times. And that's, maybe it only knows add. And that's going to be a lot slower because it's more instruction and it's going to be impacting the performance in your application. It's important for you to understand what architecture you're running on so you can then maybe use the right compiler to take advantage of those sorts of instructions. And we talked a little bit about special functions. So power, for example, is one. And a square root. There are some chips out there that have even more complicated special functions built into the hardware. So these are hardware-based special functions. But sometimes you also have to share them. And so it may be that tons of other, if you have a lot of this in your code and you're always sharing this special function piece of hardware in the architecture that you're running on, it may be that actually they may be slower because you have a lot of these sorts of calls to that specific little piece of hardware. So those are considerations you have to think about when you're compiling and architecture plus the compiler plus what you're actually writing for the compiler. So here's a Bulldozer that runs on Titan. Has a float point and an integer, a single floating point that's shared, scheduler, and then integer. And you can see the different kinds of cache and what levels of cache they are. The closer to these integer units or these floating point units, the better it can perform the calculation. So thinking about where am I, what am I doing, and how big is the memory of where I am is something that is a huge performance booster if you're writing the right code. Now, do you have to do this all the time? No, I mean, this is really about using what you have available to you. And again, a lot of the compilers can do that. A lot of the compilers will know exactly what it is that you're trying to do if you write it in a really dumb way. So here's XC30 is one of the computers that we have here, and it has that's a giant cache, and this is 20 megabyte cache. And then there's the little cores on the side have the smaller levels of cache in them. Again, thinking about cache is important. And we talked about accelerators. I don't know if you've had a chance at Lucia to talk to them about accelerators, but accelerators, again, have very, very fast memory, lots and lots of tiny, dumb little arithmetic, what they call arithmetic logic units, or tiny CPUs, if you want to think about it that way. But if you notice, all of these have to go through this PCI bus, so they have to go through, every piece of instruction has to go through your motherboard, which you all know is very, very slow, and then it has to load all those things to the accelerator. Hopefully in the future we won't have to do that. Hopefully in the future it'll be loaded directly to the hardware that you're running on, or the actual the very load straight in from maybe global memory into this. But right now it's a special offloaded accelerator that we're running. High programming model. So we went through thinking about your individual pieces of code. We went through thinking about individual instructions, how you can improve those instructions for better performance. And then the next bit that you have to think about is, well, now I want to code for a supercomputer, and what other things am I going to have to consider? Well, we talk about how there are types of supersets into the language that you can have. For example, MPI is something that is used to communicate between computers. OpenMP is something that has its own standard that's used for highly threaded programs. And so each compiler has their own implementation of OpenMP, the standard. Lots of compilers have their own implementation of the pthreads, or some compilers are specifically for shared memory or PGAS. These supersets of these languages, these added parts to these languages, can then complicate your performance also. So maybe you thought, I wrote a really super amazing Fortran piece of program, but this compiler doesn't do a very good job with OpenMP because it doesn't have maybe specific parts of the OpenMP standard that have been added. OpenMP 4.0 just came out, and I haven't really surveyed how much of that part of the standard, the new 4.0 standard, has been added by compilers. But certainly it hasn't been everything, and certainly some are doing better than others. OpenAT is the same way. So thinking about how, if you're going to do hybrid programming for a supercomputer, now not only do you have to think about the underlying language and what you've done to think about memory and data locality, but now you have to even think about standards like OpenMP, OpenACC, and other types of parallelism, hierarchical parallelism. So an idea too, and you thought perhaps, okay, I'm doing okay. I've coded my great science. It's going to, unravel all the mysteries of the universe, and I've done everything, and now I have to get to the accelerator, but I've done it only, and I've decided to choose the MPI paradigm, and now I didn't realize it, but now I have to go through this sort of proxy that is in the middle. It's a software layer in the middle between me and my accelerator. And so how can you optimize that? And so thinking about parallelism, those are things that a compiler, for example, will not pick up. There's no way that you would know simply from the compiler. This is something that happens at runtime, and it doesn't know where you're running. It's compiling for API. That's what you wrote. Understanding outside of the compiler, within the compiler is great, but understanding also how you're going to run that outside of the compiler, and how, for example, you can, in your own piece of software, try to be as asynchronous as possible to help this, would be very, very important. It doesn't matter that you came up with a very, very optimized piece of code. In the end, you might have to understand what's happening outside of the compiler that could affect your code, so that maybe you can rewrite it and think of other things. Here's another one where we're talking about OpenMP. This is adding thread, extra threads to your machine. To your piece of code. Understanding where you're running is important. If you're running on a CPU, you might only have 8 cores or maybe 16 cores. If you're running on a laptop, maybe 4 cores. The compiler doesn't know, for example, if your CPU is hyper-threaded. It's compiling for whatever it is you said it would compile for. It doesn't know that you're going to run on hyper-threaded hardware. So again, think about those things. It doesn't know, for example, if you're going to run on a mic, right? So this is OpenMP running on an accelerator that's manufactured by Intel, and in that accelerator, those individual CPUs within that accelerator, actually very low instruction CPUs. But OpenMP, you may not know that at the time, and you might have decided to, try to maybe take advantage. You might have written code that tried to take advantage of higher instruction available in the CPU, and now you're moving that, for example, to the mic accelerator, and you're doing it through OpenMP. So it may not be sophisticated enough to say, hey, what's your target? Is your target going to be a mic? And this is just a small overview of loop parallelization. I'm kind of running out of time. I'm looking at the time right now. But when you think of a loop, it's important for you to think of sort of a picture of how you're going to break down that loop. This is a very simple example of a loop over 4 cores inside your CPU, right? I have a loop that goes from 1 to 40. I can break that down really easily. But now I move that to the mic, and the mic might have 50 cores. It might have, more cores. And it doesn't make any sense for me to break up that loop in that sense, right? So are you giving it enough instruction, for example? So there was this one application I was doing, and it turned out that I had put OpenMP over a loop, and the cost for that OpenMP launch, to launch those threads for the loop, was high enough that it really didn't make a difference for the loop. It was a very tiny loop. Another thing that somebody that I was working with, for example, didn't understand is they made that so that the number of OpenMP threads was equal to 1, and their code ran slower. And it turns out that that person didn't understand, for example, that OpenMP thread launches regardless if it's just one thread, it's still a number of instructions that it's added to your machine code. So if you want to test it versus serial, an OpenMP thread equals 1 isn't the same thing as serial code because of the extra instructions that go into there to launch a single OpenMP thread. And hardware is important. The compiler you're using is important. The compiler isn't going to know that you're running a full thread, but you have 8 available. Those things the compiler isn't going to tell you. So the compiler is a miracle worker, but it's important for you to understand what parts you're writing, and perhaps you want to put some other logic in there that says, that maybe is a little more aware of the underlying hardware. There's that you can put into your code that'll say, hey, if I have more than this number of cores, this is how you're going to break down this loop, not that way, or else go to the next one. And they can do that better. So I think I only have about 10 minutes left, and I'm going to leave this open for questions.
Yeah, so I have a question. We were talking about branching, and if else statement, and there's a way to do that. What was your suggestion for optimizing that? Yeah, if and then maybe several else if. What's the better way to do that?
Depends on the application, right? The way I always try to think about it is I try to think of, can I think of a way that I can do this as a, what's the name of it? I remember I mentioned it. Sorry, I just lost the name of the. Yeah, the other type where it's not a branch. It's oh my gosh, I just lost the name. I had mentioned it during the talk where you can. No, hold on.
Prediction?
Oh. Sorry, I just lost the word. When you do, if it's 0, do this. What is that?
Switch statement?
Switch statement. Jeez Louise. Switch statement. So if you find a way to do your if-else as a switch statement, that would be the best. That's how I remove my if statements.
Better than.
Yes, strings are better than if statements.
Thank you. Any other? Are we still connected?
I'm still connected.